is for boundary problems. Okay, but instead of taking the using the reflection method that we discussed and the reflection method that works when we are that usually works when we're having a half arc, right? But if we are having whether the wave equation or the diffusion equation on only one interval, then the reflection has to be done for infinite many times, and then that usually means that the dependence, okay, of the following the following dynamics on the initial condition is going to be hardly it can hardly be determined in a very straightforward formula. Okay, so today we'll be starting from the boundary condition problems on finite intervals. Okay, and we'll be starting from the boundary problems on finite intervals, and then discuss actually one of the most general scenario. Okay, one of the most general methods to solve a linear partial differential equation, which is actually the Fourier series. Okay, also the Fourier series is going to be. Okay, that is also going to be involved. But the detail of today is only going to be a brief introduction. Actually, the whole bulk of 4.1 and 4.2 are going to be the very brief introduction, okay, to how do we apply Fourier series to solve linear partial differential equation, and the detailed mathematical discussions for the Fourier series are going to be deferred into chapter 5. Okay, so this will mostly be going into chapter 5, but we're first going to see why that works. Okay, why that works. Okay, and the idea behind the Fourier series is that's going to be actually very related to the spirit that we introduced in the first class, that the partial differential equation is actually a linear problem, a linear matrix problem, okay, but on an infinite dimension space. Okay, so that's the linear problem on infinite dimensional space. Okay, so again, let's start from simplest discussion. Okay, for the let's start from open one. Let's start from the homogeneous. Okay, let's start from the homogeneous Dirichlet conditions, which is again for the wave equation. The wave equation, UTT equals to c squared uxx, right? And again, my x belongs to only 0 and l. Okay? And I'm having my boundary condition, which is that u0t is 0, and that is also ult. Okay? And the initial condition, there are two pieces of initial condition, ux0 equals to phi x, and utx0 equals to phi. Sorry, equals to psi x. Okay? So all these things are very standard. The boundary condition, of course, so what we have done in chapter 3 for the homogeneous Dirichlet condition was that, okay, because the boundary conditions are 0 on both sides, so we are going to do reflections on both sides, and then again. Okay. Then after we extend the initial condition to the whole line, the initial condition is going to be like, okay, first of all, it's a parallelogram function for every 2L, every interval 2L. And second, for inside every interval of 2L is actually symmetric, okay, towards 0 or towards L, right? Okay. So that usually means that when we are solving the wave equation, we need to find the solution. Okay, if you still remember the solution the exact solution will depend on, okay, that will be depending on the number of reflections, right? The number of reflections that the system has experienced, right? So this is 0, this is L, and this is the time t, right? If I'm starting from some time over here, then, well, no reflection at all. If I'm starting from some time at here, then there's going to be no reflection on the right side, but one reflection on the left side. If I'm starting from here, then there's going to be reflection, okay, reflection and reflection, 2 reflections on the left side, and also 2 reflections on the right side. Right? Okay. Then the specific solution will be depending on the number of reflections. Okay. And the number of reflections will be determined by which zoom, okay, is for the xt on the strip. Okay. On the strip. If my xt is over here, then the number of reflections is going to be 1 and 1. Over here it's going to be 2 and 1, 1 and 2, 2 and 2, okay, and then 3 and 2, 2 and 3, 3 and 3, so on and so forth, right? And that means that the expression of the specific solution for any particular x and t, that will depends on the location of x and t, and actually creates extra inconvenience for us to write down the formula. And what we're proposing to do today, okay, is going to be first of all an introduction for a method, okay, for a new method, let's say. A new method that is called the separation separation of variables. Okay, that's going to be the separation of variables. And the narrative of the separation of variables goes as follows, okay, at least according to the book. What is that? Okay, so first of all, the uxt, right, the uxt, we have no reason to believe that the uxt could be separated as the product, okay, of 2 functions, that one is only depending on x, another one is only depending on t, okay? But let's just try it at first. Okay, so that, which means that I first assume, okay, I assume. Again, this assumption doesn't have to be true at all. We first assume that uxt, okay, is the product of 2 one-dimensional functions. One of it is about x, okay, and another one of it is about t. Okay. Again, this is the assumption. I assume that uxt could be written, okay, into xx multiplied by tt, okay, or in the so I know that some of you are actually a lot of you are actually right now taking probability, right? You're taking probability, and for the other people, we have already taken probability. So I can safely use the analogy for the independent variables, right? Imagine that I have a joint probability distribution, which is called U, okay? And that depends on 2 random variables, x and t. The fact or the phenomena that uxt can be written into a product between 2 marginal variables or 2 marginal distributions. One is only about x and another one is only about t. That means what? That means that these 2 random variables are completely independent. Okay? So these are the same. Okay? These are the same arguments. Okay? These are the same arguments. So here, but the question is what? The question is that, you see, for any 2 random variables, they don't, without any information given at the beginning, okay, we cannot assume that they are independent at all. Okay? Because we just don't know. We just cannot be sure. Here, again, without any information given at the beginning, I cannot assume, I cannot say that UXT can be separated into these two variables, right? Because they can of course be coupled, okay, in a much complicated fashion. And actually, if you go back to see your previous answers to questions, okay, to questions about wave equations, you're going to see that, well, your answer, in most of your answer, okay, your solution UXT is not separable. It's not separable. Then the question comes, right? Why do we want to do this? Okay, why do we want to assume something that seems to be nothing that's good for us? Why do we choose to go this route? Okay, well, the answer is the following. Okay, the answer is the following because I really thought hard about how to deliver this class. Okay, to make it to be more reasonable for everyone. The answer is the following. So let's come back to look into the. Let's come back to look into the equation itself. Okay, let me write the equation over here. So it's actually UTT equals to C squared UXX. So that's good. Okay. Well, again, of course, my U is a function that's on both X and T. Okay. And UTT is what? The second, this is actually the second order derivative on time for U, right? So let me just write it down as something like, okay, partial square U and partial T squared, okay, equals to C squared, and then partial square U over partial X squared. So that's good. Okay, this is again, I'm just simply writing this equation again. Well, what is the left hand side? What is the left hand side? And what is the right hand side? The left hand side is actually a linear differential operator, okay, towards U. The right hand side is also a linear differential operator towards U. So what's it? So that means that I am looking into, I'm actually, again, imagine my U is a vector. Now imagine my U is a vector, although it is not, okay, U is a function, but imagine that my U is a vector. Then the left hand side is equivalent to something like, okay, let's say AU. A is a matrix. Okay, if my U is an n by n, is an n-dimensional vector, then my A is a n by n matrix. Okay, AU equals to something like C squared BU. So as a good, AU equals to C squared BU. Okay. Well, if this is a linear problem, how do you solve it? If this is a linear problem, how do you solve it?
A minus C squared B.
Sorry? A minus C squared B, okay. But the problem is what? The problem is that I have no information about the inner structure of A and B. Right? So can anyone tell me, okay, if I use the two matrices to represent the partial derivatives, okay, what should it be? Then how to write down the matrix? We have no information for that, right? I have no information for that. But another way to do this is that, okay, suppose that I am looking into the eigenvalue problem. Suppose I'm looking into the eigenvalue problems. Okay, suppose I'm looking into the eigenvalue problems for A and B. Okay, suppose I'm trying to do that. Because if I am looking into the eigenvalue problems for A and B, then first of all, okay, the eigenvalues for A and the eigenvalue and eigenvectors for A and B can be something like, okay, so first of all, let's say AU equals to number U. Okay, and BU equals to eta U. Oh, sorry, let me write this again. Eta U. Okay, AU equals to lambda U and BU equals to eta. If I am able to find let's say, if I am able to find certain eigenvector, okay, certain vector that can serve as the eigenvector of both A and B, right? That can solve my problem. That can solve my problem, right? And specifically, if I could find. So the question is that the new question is that how to find an eigenvector U, okay, such that okay, the U is the eigenvector for both okay, A and B. U is the eigenvector for both A and B. And okay, my lambda exactly equals to C squared eta. Okay, I just need to look for an eigenvector as this. If I can find it, so first of all, the answer doesn't have to be only one eigenvector. Okay, the answer doesn't have to be only one eigenvector. But if I can find one eigenvector that satisfies this, okay, then my eigenvector will be supporting my eigenvector will be a solution to the linear equation AU that equals to C squared B, right? And there is actually another issue about the eigenvector. Okay, there is another issue about the eigenvector. That is, what is the property? First of all, what is the property of A and B? Okay, what is the property of A and B? Well, you see, let's say if a matrix, let me not use A and B, okay? If a matrix M satisfy that my M equals to M transpose, then what type of matrix is M? If my M satisfy that M equals to M transpose, what kind of matrix is M?
Square matrix.
Sorry?
Square matrix.
Sorry. M is what kind of matrix?
Square matrix.
A square matrix, of course, that should be square matrix, and what else? Any square matrix can satisfy M equals to M transpose?
Symmetric
Okay.
over the
Symmetric,
diagonal.
right. M should be a symmetric. What property does a symmetric, what property does the eigenvectors of a symmetric matrix have? What property does the eigenvectors of a symmetric matrix have?
Always.
They should be always orthogonal to each other. Right? They should always be orthogonal to each other. If you don't believe this, okay, you don't believe this, well, let's say I'm having my let's say I'm having my MB, okay, my MB, which equals to number 1B, and my MC equals to number 2C. Okay, so that's good. Well, what can you say for let's say for C transpose multiplied by MB? What can you say about C transpose? What can you say about C transpose multiplied by MB? Okay, so that should equals to if I am because the matrix I can do the matrix multiplication I can write my brackets everywhere, right? Okay. So that means that this on the one hand equals to C transpose, okay, multiplied by MB, right? Okay, that also equals to C transpose M multiplied by B. So far so good? So far so good? Okay, well, what is this? What is the first modification? What is NB? That's lambda 1b, right? But lambda is what? Lambda is a value. Lambda is a value, so that's actually lambda 1 multiplied by C transpose multiplied by B. Okay? What about the second one? What is C transpose multiplied by M? What is C transpose multiplied by M? That's actually M transpose C transpose. So far so good? And then multiplied by B. But what is the MC what is M transpose? It's M itself, right? So this is actually MC, but what is MC? It's number 2C, right? It's number 2C, which is number 2C transpose multiplied by B. So what does that mean? What does that mean?
Oh, if lambda 1 doesn't equal to lambda 2,
Okay.
then
Either my number 1 equals to number 2, then this is okay. If my number 1 doesn't equals to number 2, then the only way for this equation to hold is that my C transpose B is what?
also
Goes to 0.
oh,
Okay. Then that means that for any two eigenvectors that are not sharing the same eigenvalues for a symmetric matrix, they should be what? They should be orthogonal to each other. Okay. So the argument is that. So this lecture should have been given by your linear algebra teacher, right? So the argument is that for any eigenvectors different for any different eigenvectors with different of M with different eigenvalues, they should be orthogonal to each other. They should be orthogonal to each other. Okay? They should be orthogonal to each other. Well, if my M, this is my argument 1, if my M is a symmetric matrix, what other properties does a symmetric matrix have? What other properties about eigenvectors, specifically about eigenvectors and eigenvectors, does a symmetric matrix have? Any symmetric matrix, is always what? It's guaranteed to be what? It's guaranteed to be diagonalizable, right? My matrix, my M is, this is my argument 1, and my argument 2. Argument 2 is that, M is guaranteed to be diagonalizable. That means that there has to be something like, let's say S, there has to be S such that a matrix S such that S and S transpose, exactly equals to a diagonal matrix D, which is exactly my number 1, number 2, until number n. And the column vector for S, is exactly the eigenvectors for n. So that's good? That's good? Okay. So now, my M is guaranteed to be diagonalizable. That means what? That means that it is guaranteed to have n different eigenvectors. It's guaranteed to have n different eigenvectors. And also we know that the eigenvalues, any different eigenvectors for n are guaranteed to be what? Are guaranteed to be orthogonal to each other. So that means what? That means that my S,
is also
my S is essentially my S1, S2 until Sn. Okay, all these S are eigenvectors for n, right? And these eigenvectors are guaranteed to be what? To be orthogonal, right? My Si and Sj are guaranteed to be orthogonal to each other. This is how many dimensional space? This is n-dimensional space. And now I have n eigenvectors that are orthogonal to each other. So this is actually what? Is actually what? Is actually a orthogonal basis. This is actually an orthogonal basis. This is an orthogonal basis. So that means that my S1, S2 until Sn is an orthogonal basis, okay, of Rn, of the whole space. So good? So good? Okay, well, you see, let's go back to our origin, right? Okay, so you see, the property of A and B, and then I very abruptly jump to a new topic, right? That my M is symmetric, is a symmetric matrix, right? And such that my M equals to M adjoint, or M actually equals to M transpose, right? And why did I do that? Well, the reason is that the same property applies here, okay? The second order partial derivative, okay? The second order partial derivative exactly satisfy that when regarded as a matrix, okay, when regarded as an operator, okay, the second order differential operator, okay, these things are exactly, okay, symmetric to each other, or self-adjoint. Symmetric matrix this also can be so let me write one more argument over here. Symmetric means that self-adjoint. Okay, I suppose you know the idea about self-adjoint, right, and self-adjoint. Okay, in your linear algebra class, right? Okay, how do we see that how do we see that the second order derivatives of t and second order derivatives of x are indeed self-adjoint linear operators? Well, okay, this is indeed a little bit hard. Okay, but let me do the following. Okay. Okay, so now the new argument is that u, okay, so let's say A that equals to partial square partial t square, and B that equals to partial square, okay, partial x square, okay, are indeed self-adjoint. Operators. Okay, so argument. A and B, they are indeed self-adjoint operators. How do we show that? Well, you see, how do we argue make the argument for the symmetric matrix? We talked about the inner product. We actually talked about the inner product between vectors, right? So when we are trying to argue that A and B, they are indeed self-adjoint operators, we also need to talk about the inner product. But here, the inner product for a function, for inner product of function. So let's say I am talking about any function of fx. Okay, let's consider I'm having a function that's about x, fx and gx. Okay, so inner product. Okay, inner product about fx and gx. Well, how to define the inner product between two functions, fx and gx? Suppose that here again my x is again defined on 0 and L. How do I define the inner product between two functions?
Integral.
How to define the inner product of two functions? Well, okay, so now I probably have to use this one. You see, again, how did I define the inner product of two vectors, right? I was defining, so let's say I'm having my let's say my B, okay, which equals to something like B1, B2, and until Bn, right? And I'm having my C that equals to C1, C1, C2, and until Cn. Okay, how did I define the inner product for B2, B, and C?
B1 C1 plus B2 C.
Okay, I just combine and I just see, okay, so the first dimension, the first entry multiplied by each other, with each other, and the second entry multiplied with each other, and finally the nth entry multiplied with each other, and then we finally all added up. Okay? Now, let's say I'm having two functions. Both of these two functions, this is my fx, this is my gx. Okay? My fx is something like this. Okay? That's between 0 and L. 0 and L. Okay, 0 and L. Then my gx is something like this. How to define the inner product between fx and gx? Okay, so an intuitive way goes like the following. Let's again cut each function into pieces. Let's again cut each function into pieces, right? Okay, so now, and so this is the first piece. Let's say this is delta x, okay, and 2 delta x, okay, and the third piece, and finally the nth piece. And I'm having my case piece. So now, let's say this whole function is approximately represented by these pieces, and assume that each piece is actually constant within each interval. Okay, assume that each piece is actually constant. Now, my fx is essentially represented by what? By f1, f2, to fn, right? If they are indeed n intervals. If they are indeed n intervals. So far so good? And what about my gx? My gx is now represented as g1, g2, until gn. So f1 is exactly the value of f in this interval. f2 is exactly the value of f in this interval. f3 until fn. g1, the value of g in this interval. g2 is the value of g in this interval. And here, gn, the value of g in this interval. So far so good? So now my f and g, they are approximately two n-dimensional vectors. How do we define the inner product between f and g? There has to be something that's close to what? f1 multiplied by g1 and then plus f2 multiplied by g2 and then plus f3 multiplied by g3 and finally fn multiplied by gn, right? But that depends on what? That depends on how do I cut up these two functions? How do I cut up these two functions? Right? So this is essentially, so if I let me write it on the board. So let me write it over here. Let's say my fx, okay, is something like this. My gx is something like this. Okay, so this is my f1, this is my g1, this is my f2, this is my g2, and so on and so forth, so on and so forth. Okay, sorry, it has to be at the same length. Okay, and this is my fn, this is my gn. So my f, the inner product. Okay, the inner product of f and g. Okay. Of f and g can be represented as something like, let's say the bracket, okay, round bracket, f and g, okay, represented as, okay, f1 multiplied by g1 and then plus f2 multiplied by g2 and then plus da 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 da, and until fn multiplied by gn. Sounds good? Okay. But again, this depends on what? This depends on how do I cut it up. The number of pieces. If the n goes to infinity, then what should this kind of things, I mean, what is the limit of this kind of things?
The integral.
Certain integral, right?
F.
Right. Then when n goes to infinity, okay, these things will be converging to something like from 0 to L my fx gx dx. This is also what? This is also the corresponding value. First of all, the corresponding value of f and g, first of all, multiplied by each other, and then added up. But it's just now that the added up process is now replaced by what? Replaced by the integral. So that's good? Okay, so this is how we define the inner product between two functions. Okay, now I need to come back to use the idea of inner product to argue that A is indeed the self-adjoint operator. And B is also, again, the self-adjoint operator. Okay, the self-adjoint operator. How to do that? How to do that? Well, self-adjoint, again, coming back to that case. How to argue? Question. How to argue that, that's for example, B, okay, which is that partial, the second order of spatial derivative, okay? How to argue that B is self-adjoint? How to argue that it's self-adjoint? Well, when B, if B was a matrix, what do we do? If B was a matrix, then B is self-adjoint, is equivalent to what? Is equivalent to that for any two vectors. Okay, for any two vectors, let's say f and g, my f, the inner product between f and b and bg, okay, which is exactly the which is exactly the f transpose, okay, f transpose multiplied by bg, because b exactly equals to its transpose. Right, B is self-adjoint. B exactly equals to its transpose. That should equals to F transpose B transpose G. Right, and which equals to BF transpose multiplied by G. Is that right? But what kind of inner product is this? This is exactly the inner product of B, F, and G. Right? So again, B is self-adjoint is equivalent to that for any two vectors f and g, that the inner product between f and bg is exactly the inner product between b and g. So it's okay? This step is okay? This step is okay? Okay. So similarly, now b is equals to partial derivative. The way to argue that my partial derivative is indeed self-adjoint, okay, the way to argue that my b is indeed self-adjoint, okay, can be done as follows. Then again, b is self-adjoint. Okay, b is self-adjoint is indeed, okay, can be argued in that for any two functions, okay, for any two functions, fx and gx, okay, for any two functions, fx and gx, that belongs to, that where my x belongs to 0 and L, okay, I need to argue that again, the inner product between fx and bgx exactly equals to bfx and gx. Okay. I need to argue this. to show that indeed that my B is self-adjoint. My B is self-adjoint. Is that true? Well, first of all, what is the inner product between fx and bgx? What is the inner product between fx and bgx according to what we have discussed over here? What is the inner product between fx and bgx? That should be exactly the what? This is how we do an inner product between two functions. How do we do inner product between fx and bgx? That should be what? That should be the integration of what? From what to what?
From 0 to L.
Integration from where to where?
From 0 to L.
From 0 to L, okay, and then what? Fx
Times
multiplied by
G
bgx. But what is b?
G prime.
Okay, that's the partial x squared, right? And then what? Gx. This action upon gx, right? And then dx. So this represents the first inner product. We want to prove what? We want to prove that this is indeed equals to from 0 to L. What is the second inner product? What is the second inner product?
Partial square product.
Okay, it should be partial x, okay, second order derivative of f, okay, and then multiply by g dx. We want to show that these two integrals indeed equals to each other. Okay, this is actually not hard to show by the integration by parts, but actually we need one more thing. There's one more thing missing. If we continue to do the integration by parts. Because of what? Because okay, so now let's say because of what? Because well, okay, so now f and g, both of them they are only functions for x, right? So the partial derivative is actually the whole derivative.
Oh.
Right. The partial derivative is actually only the derivatives for x. Okay. So if I want to move the partial derivative from g to partial derivative to x, then of course I have to do integration by parts. Right? I have to do integration by parts. Well. By doing integration by parts for the first one, what do I do? What do I get? So okay, so that's integration from 0 to L, fx, and then d, okay, and then d, and then it's going to be dgx over dx. It's going to be something like this, right? Then that equals to dgx, okay, multiplied over dx multiplied by fx, and evaluated from 0 to L, and then minus 0 to L, and then dgx over dx, and over dfx. It's something like this, right? And then I have to do one more step. I have to do one more step, which is dgx, okay, over dx, and then multiplied by fx, evaluated from 0 to L, and then now minus dgx. Another time we division by parts, multiplied by dfx, okay, over dx, evaluated from 0 to L, and then plus, okay, from 0 to L, now gx multiplied by the second order derivative of fx dx, which, well, the last part is exactly this guy, right? The last part is exactly our target. But we're having two very fussy first part, right? We're having two very fussy first part, right? So, so don't forget, okay? Don't forget what was the boundary condition.
0.
What was the boundary condition?
0.
Boundary condition tells you that it vanishes on the boundary. Okay? The boundary condition tells you that it vanishes on the boundary. So over here, okay, over here, one more one implicit requirement for fx and gx is that okay, my fx and gx vanishes on the boundary. Okay, it should vanishes on the boundary. Okay, so well, okay, you see. We have actually argued two things. Okay? If I zoom out a little bit, we have actually argued two things. two flows, okay? This flow, over this flow, we argue things that, okay, if a operator is self-adjoint, okay, then it's, first of all, then it's all, I mean, the whole set of its eigenvectors can form a orthogonal basis of the whole space. Argument number one. And the argument number two is that, okay, the second order partial derivatives, A and B, they are indeed what? They are indeed, okay, these two things, they are indeed self-adjoint. Self-adjoint. Therefore, that means that, that means what? Therefore, that means that the, okay, these two things come together, okay, these two lines come together. So I need to draw very two big. So one thing is about this, okay, and another thing is about this. Okay, these two things. Okay, these two things. These two things. Okay, come together. They support. Okay, they support one argument that the self, okay, sorry, the eigenvectors of ut, sorry, the eigenvectors of second order derivative on time and second order derivatives on space, okay, indeed form an orthogonal basis of the whole space. What space? Then the question is, first of all, what are the eigenvectors? And second, what are the whole space? What are the eigenvectors and what are the whole space? Since we're not talking about matrix and vector anymore, the eigenvectors, the so-called eigenvectors of the differential operators are actually what? Are eigenvectors. They're not eigenvectors. These things are not vectors. Simply because what? Because the operators, they are not taking actions upon vectors. They are taking actions upon what? Functions. So instead of eigenvectors, what should I say? Eigenfunction. Okay, this is indeed the formal name. Okay, this is indeed the formal name. So the eigenfunctions. Okay, the eigenfunctions. And second, what is the so-called whole space?
All the functions.
This should be the space of what?
All the functions.
All the function. What kind of function? All the functions are everywhere.
On 0 to
Where is the function defined?
Solutions.
Where is the function defined? Where is this function defined? Where is uxt defined?
0.
0
x should be belong to what? Belong to 0 to L. And t should be belong to what? From negative infinity to positive infinity. Right? Okay. So what is the whole space over here? The whole space, okay? The whole space is, okay, functions. Actually, not all the functions, and actually, you should have to, actually should be some relevant functions, but again, I cannot say too much about this before we talk about anything about in the function analysis. But let's say the whole space is the space of function, the space of functions, okay, on the strip, the xt belongs to 0 to L, and then from negative infinity to positive infinity. Is that all? Is that all the requirements for the function? Is that all the requirements for the function? What else did we do? What else did we use when we are arguing the self-adjointness for A and B? Is that all? Can the value of the functions of u and t be arbitrary on the boundaries? No, they should be what?
It should be
It
0 on the boundary.
Okay. And such that, okay, on the strip, the space of functions on the strip such that, okay, u 0 t always equals to 0, and u l t always equals to 0. Okay? So that's good? So that's good? Okay. So now, okay, with this in mind that, first of all, the analogy in linear algebra, okay, it suggests us to to seek the eigenfunctions, okay, the eigenfunctions for the eigenfunctions for these two operators, okay. So indeed, we would like to seek for the eigenfunctions for these two operators. And second, we also know that the complete set of eigenfunctions for these two operators, they satisfy what? They form the basis of the whole space. They form the spaces of the whole space. That means what? That means that any eligible function, okay, any eligible solution, and okay, any solution uxt, because you see, if I want a function to be the solution, it should be what? It should be at least. It should be at least. I mean, an element in the whole space, right? Okay. Then that means that any solution uxt can be expressed as what? What is it by orthogonal basis mean? An orthogonal basis has the power to do what? An orthogonal basis has the power to represent what? To represent anything in the whole linear space, right? That means that any solution ut, because it exactly have to be one, and it has to be one element in the space of the function. Therefore, okay, any solution ut can be represented by what? By the linear combination of these eigenfunctions. So that's good. Okay. Then the argument is that any solution uxt can be okay, represented by the linear combination of the eigenfunctions of partial t squared and partial x squared. So we are taking 1 hour to go to arrive to this argument. And what does the book do? Okay, what does the book do? The book just simply it's just simply goes from here. Okay, it just simply goes from here, and it has nothing below. Okay, the book goes from here. Okay, it has nothing below, and it tells you that okay, so now we seek for the corresponding x and t. Okay, and then we have many choices. We are going to see that we have many choices for the functions xx and tt. Okay, and their linear combination is going to form. Okay, the linear combination is going to form our solution, and that indeed has the reason. What is the reason? The reason is exactly what we have gone through in the last hour. It's all over here. Okay, it's all over here. This is the reason. This is the reason behind it. And I always would like you to understand what is the reason, although this is not completely mathematical rigorous. Okay, but this is the reason behind it. Okay? So, you say after we are done with the reasoning, then the rest is just simply the computation. Okay, and I am going to finish the computation in 5 minutes. Okay, in 5 minutes from now. So what is that? You see again now coming back to computation. Okay, now coming back to computation. You see, what did I do? What I did was uxt, okay, that equals to x, and multiplied by t, right? And specifically, I would like my xx to be an eigenfunction for partial x squared. okay? And my tt to be an eigenfunction for partial t squared. What is the reasoning behind it? Well, you see, if my uxt is expressed as this, first of all, you see, because my u should be the solution to utt equals to c squared uxx, right? So question number one, what is utt? What is utt? What is utt?
Big X times
Okay,
big
x multiplied by what? T prime prime. T, right? Okay, so that's good. What is my uxx?
Big X prime.
X prime prime, x multiplied by t, right? So that's good. So what are the relation between them?
C squared.
Okay, the relation between them is exactly that. Okay, so now the x, I'm going to say the independent variables, right? So x t prime prime should exactly equals to c squared x prime prime t, right? Again, not separation of variables, but the separation of the functions. Now what we're having is exactly that. Okay, the t prime prime over c squared t, okay, equals to x prime prime over x. Oh, sorry, there's no negative symbol. Right? I'm just doing the separation of okay? So now if my x and t, if they are eigenfunctions, if x is the eigenfunctions of the partial derivative, x and t is the eigenfunction for the partial derivative of t, what do we obtain? Well, then that means that, okay, my x prime prime is going to be a certain fold of x, and my t prime prime is also going to be a certain fold of t, right? Okay, because of, and this has to be true. This actually has to be true because of what? Because you see, what is on the left hand side? This is a function of t. This is a function of t. This is a function of x. This is a function of x, right? This is a function of t, and this is a function of t. So the left hand side is what?
A function.
A function of t. This is a function of x. This is a function of x. So the right hand side is what? A function of x. You see, the left hand side is only a function of t, and the right hand side is only a function of x. What kind of things can satisfy that? Only constant. If that is a constant, and I call it as, let's say, negative lambda, and I'm going to tell you why do I want a negative sign later, okay? If that has to be a constant, then what is my t and what is my x? Then actually that means that it tells me that, okay, t prime prime over t, that actually tells me that, okay, t prime prime equals to negative lambda c squared t, right? And then x prime prime equals to negative lambda x. So far so good? Okay, so far so good? Well, now, what do we have? T is what? Now T is what? T is an eigenfunction for second order derivative, right? Because second order derivative actioning upon t, I obtain a fold, okay, and multiples of t, okay? And second order derivative of x actioning upon x, I obtain a multiples of x, okay? So indeed, my x and t, they are indeed the eigenfunctions for the partial x squared and partial t squared. Okay. Well, then what kind of functions? What exactly are they? What kind of function exactly are they? Okay. Then let's see. Probably I'm going to let's stop here and then let's take 5 minutes break, and then we can use another 20 minutes to finish this discussion.